Let's see how quickly we can cover everything you need to know for GCSE Chemistry Paper 1 for OCR. This is good for higher and foundation tier, double combined and triple separate science. I'll tell you when some of the bigger concepts are for triple, but not what's for higher and foundation, as there's not a lot of difference honestly. And don't forget to check out the Science Shorts app to help you test your knowledge. Let's go. Substances, stuff, are made of atoms. The different types or elements of atoms are represented in the periodic table by symbols. A compound is a substance that contains two or more different types of atoms chemically bonded together. For example, the chemical formula for water is H2O. Every molecule of water is made of 2 hydrogen atoms and 1 oxygen atom. These atoms change what they're bonded to and how they're bonded through chemical reactions. We can represent a reaction with a word equation or a chemical equation using symbols. As atoms are not created or destroyed in a chemical reaction, there must be the same number of each type of atom on both sides. So sometimes we have to balance equations. Pro tip, start balancing atoms that are only in compounds. So with this one, let's go with the carbons first. There's 1 on the left, 1 on the right, so that's all good. Hydrogens, however, there are 4 on the left, only 2 on the right. Now, we can't change the small numbers because that would change what the compound is. So all we can do is put numbers in front of elements or compounds to multiply them up. Stick a 2 in front of the H2O, we now have 2 times 2 hydrogens, so that's 4 on the right as well. That's also doubled the oxygen in it, however, so we now have 4 oxygens altogether on the right, still only 2 on the left, so doubling the O2 on the left takes care of that. If there's an element in a reaction, like the oxygen here, we always balance that last as there's no knock-on effect then. A mixture is any combination of different types of elements and compounds that aren't chemically bonded together. For example, air is a mixture of oxygen, nitrogen, carbon dioxide and more. Solutions are mixtures too, like salt water. It's a mixture of water and sodium chloride. The sodium chloride is dissolved in the water. You can't see it. You can separate large insoluble particles from a liquid using filtration, like sand from water, as sand can't dissolve in water. Crystallization can leave a solute, that's the solid dissolved in a liquid, behind as you evaporate the solvent from a solution, like evaporating water from salt solution, leaving only salt crystals behind. Similarly, distillation involves heating the solution as well, but this time the gas is cooled, so it condenses back into a liquid. You can also do this at different temperatures to separate the different liquids of a mixture, as they'll have different boiling points. This is called fractional distillation. These are all physical processes though, and not chemical reactions because no new substances are being made. Obtaining pure substances is very important when it comes to chemistry. One way to tell if a substance is pure or not is by testing to see what its melting point or boiling point is. If it's pure, it should be a very specific temperature. If it doesn't melt or boil at the temperature that you thought, then it's impure. There are impurities in it. A formulation is a mixture that has been specially designed to be useful in a very specific way, with very specific quantities of different substances used to make things like paints, fuels, alloys, fertilizers, etc. Think of George's Marvelous Medicine as being the ultimate formulation. Chromatography is a way of separating substances in a mixture, for example, pigments in inks or drugs in a urine sample. The stationary phase, often special chromatography paper or just filter paper, is what the substances move up, with the help of the mobile phase, often just water, which rises up the paper due to capillary action, dragging lighter particles further up the stationary phase. We draw the line at the bottom in pencil so it doesn't move with the mobile phase, the water. Then at the end of the process, we measure how far the mobile phase has moved and also how far the substances have moved too. These are both measured from the starting line. We can then calculate an RF value, that stands for retention factor, for each spot. That's just a ratio of how far a substance, a spot, has moved compared to the mobile phase. So it ends up being a number between 0 and 1. We can then compare RF values of our spots with known RF values to identify what's in our mixture. Solid, liquid and gas are the 3 main states of matter. For example, water can be ice, a solid, where the particles or molecules in this case vibrate about fixed positions. It can also be liquid water, when the molecules are still touching but are free to move past each other. And it can be gas, water vapor we call it when it's water, where the particles are far apart and move randomly, and they also have the most energy and so move quickly. As molecules in a gas are far apart, gases can be compressed while solids and liquids cannot. To melt or evaporate a substance, you must supply energy, usually in the form of heat, to overcome the electrostatic forces of attraction between the particles. We don't say we're breaking bonds in this case though. Note that none of these make a new substance, so these have to be physical changes. We indicate what state substances are in with state symbols. Brackets S for solid, L for liquid, G for gas, and AQ for aqueous. That means dissolved or in solution, again like salt in water. The idea of what atoms are like came about gradually. J.J. Thomson discovered that atoms are made up of positive and negative charges. He came up with the plum pudding model of the atom, a positive charge with lots of little negative charges dotted around it, electrons. It was then Ernest Rutherford who found that the positive charge must actually be incredibly small. We now call this the nucleus. He discovered this by finding that most alpha particles fired at a thin leaf of gold atoms went straight through, proving that atoms must be mostly empty space. Niels Bohr later discovered that electrons exist in shells or orbitals. Then James Chadwick discovered that the nucleus must also contain some neutral charges. We call these neutrons, while the positive charges in the nucleus are called protons. Protons and electrons have equal and opposite charges, so we just say they're +1 and -1, relatively. Neutrons have a charge of 0. Protons and neutrons have essentially the same mass, so we say they have a relative mass of 1. Electrons are very light in comparison, so we say they have a mass of 0 or just very small, depending on the situation. The periodic table tells us everything we need to know about an atom. The bottom number is the atomic number, that's the number of protons in the nucleus. That determines what element an atom is. Every atom has an overall neutral charge, so that must mean that they have the same number of electrons as protons. If an atom gains or loses electrons, it's now called an ion, not an atom. The top number is the mass number, or relative atomic mass, or RAM for short. It tells you how many protons and neutrons are in the nucleus, so that must mean that this carbon atom, carbon 12, has 6 neutrons on top of its 6 protons to make that 12. However, you can get a carbon atom with 7 neutrons instead, so its relative mass is 13. These are what we call isotopes, atoms of the same element but with different numbers of neutrons. You might see a mass number that isn't a whole number. This is because periodic tables sometimes show the average mass for all of the isotopes of that element found in the world. For example, if you have some chlorine gas, it turns out that 75% of the atoms will have a mass of 35, while 25% of the atoms will be 37. This is what we call their relative abundance. To find the average, we just pretend that we have 100 atoms. We add up the total masses of all the isotopes, then just divide by 100. That's why chlorine's average relative atomic mass is 35.5. The periodic table is incredibly useful, but how was it made? Before it, scientists just put elements in order of their atomic weight. Some were then grouped together if they were seen to have similar properties, but still using the atomic weight order. Dmitry Mendeleev then came along and grouped elements together based on their properties, even if the order didn't follow atomic weight. Using this method, he found there were gaps in the table. He asserted that these elements were yet to be discovered, and in time, he was proven right, showing that his table was indeed correct. Electrons exist in shells around the nucleus. The shells fill up from the inside, with a maximum of 2 electrons on the first shell, 8 on the second, and 8 on the third shell, then we only go to 2 on the fourth shell. That's 20 electrons altogether, which brings us to a calcium atom. After this, we get into the transition metals, where things get a little bit crazy, so we leave that for A-level chemistry. So we only care about the electron configurations going up to 2882. Magnesium has 12 electrons, so its electron configuration must be 282. The periodic table can be split up into different bits. For example, everything to the left of this staircase is called a metal. Metal atoms always donate electrons when they bond to gain an empty outer shell of electrons. Again, transition metals are weird, but we don't think about their shells for now. To the right of the staircase, non-metals. They always accept electrons to gain a full outer shell. The column an atom is in is called its group. It tells you how many electrons an atom has in its outer shell. Again, the transition metals work in a really weird way, so they don't get their own groups. In fact, it turns out this is because they can donate a different number of electrons depending on what they're bonding to. The atoms in group 1 are called the alkali metals. They all have 1 electron in their outer shell, which they give away or donate when they bond to something, so they all have similar properties, like when they react with water. The further down the group you go, though, the further that outer electron is from the nucleus, so the electrostatic attraction is weaker between the negative electron and the positive nucleus. This means that the electron is more easily donated. This means the metals get more reactive as you go down the group. Group 7 are what we call the halogens. They're essentially the opposite. They have 7 electrons in their outer shell, so they need 1 more electron to gain a full outer shell. The further down the group you go, the less readily an electron is accepted onto that shell that's further away from the nucleus, so they get less reactive down the group. Their boiling points also increase down the group. Group 0, sometimes referred to as Group 8, are called the noble gases. They already have an empty or full outer shell, depending on your perspective, so they don't react. Well, in reality, sometimes they can react under special conditions, so we just say they're very unreactive. We don't really say Group 8 anymore though, because some people thought that helium might feel a little left out, as it only has 2 electrons in its outer shell. As electrons are negative themselves, metals become positively charged when they lose them. Metals always form positive ions. All of Group 1 lose 1 electron when they turn into an ion, so all of their ions are 1+, but again we don't write the 1, we just put plus. Group 2 lose 2 electrons to get an empty outer shell, so their ions are all 2+. Group 7 gain 1 electron each, so all of their ions are -1, just minus. Group 6 ions are all 2-. The atoms in Group 3, 4 and 5 don't really form ions, except for aluminium, which is 3+. Like we said, transition metals can donate different numbers of electrons. For example, an iron ion can be Fe2+, or Fe3+. It can donate 2 or 3 electrons depending on the situation. So we give the ions the name iron 2, the 2 in brackets, and iron 3 to distinguish between them. Transition metals are generally harder and less reactive than other metals. They also form coloured compounds. Bonding next. Metal atoms bond to each other through metallic bonding. Essentially, a lattice or grid of ions is formed with a sea of delocalized electrons around them. Delocalized just means they're not exactly on the atom anymore. As these electrons are free to move, metals make good conductors of electricity and heat. Metals bond to non-metals through ionic bonding. Like we said, a Group 1 metal needs to lose an electron while a Group 7 atom needs to gain one. It's a match made in heaven. For example, a lithium atom donates or loans its outer electron to the chlorine atom. We can draw a dot and cross diagram to show where the electrons end up. We only need to draw the outer shell for each of these. Don't forget to put brackets and the charge of the ions too. When it comes to ionic bonding, the charges of all ions in an ionic compound must add up to 0. So Li plus and Cl minus is all good. So this is the chemical formula for lithium chloride. The same with beryllium oxide. Be2 plus and O2 minus, so it's just BeO. Beryllium chloride, on the other hand, well, the beryllium needs to lose 2 electrons while a chlorine atom only needs 1. So that means there must be 2 chlorines or chloride ions for every beryllium. So Be2 plus and 2 lots of Cl minus add up to 0. So that means the chemical formula is BeCl2. Sorted. Ionic compounds consist of lots of repeating units of these ions in a lattice to form a crystal. They have high melting points and boiling points due to the strong electrostatic forces that need to be overcome. They can conduct electricity, but only when they're in liquid form, that is molten, or dissolved in solution. That's because the ions are free to move in both cases, and they carry charge. You can also get molecular ions. For example, OH- is a hydroxide ion. It consists of a hydrogen atom and an oxygen atom. Here are a few other examples. By the way, I still spell sulfate with a PH instead of an F because I'm stubborn and refuse to adopt the American spelling. You'll get the mark either way. Any ionic compound can be called a salt, not only sodium chloride, table salt. The name is always the metal ion, positive ion, or cation we can call it, followed by the non-metal ion, or anion. Anion names are different from their normal names, like we've just seen, so it's not sodium chlorine, but sodium chloride. Some people find it helpful to remember which way round cations and anions are by liking cats, which can be nice creatures sometimes. They say cations are positive or positive. Non-metals bond to each other with covalent bonding to form molecules. They do this by sharing electrons to gain full outer shells. For example, chlorine gas is Cl2. Each chlorine atom shares an electron with the other, so they both have full outer shells. So they're both happy. Never write that in the exam though. Here's the dot and cross diagram. We can also draw the structural formula for molecules with just symbols and lines representing the covalent bonds. We say that every one of these covalent bonds represents a dot-cross electron pair. Each oxygen atom needs 2 extra electrons, so O2 is a result of each oxygen atom sharing 2 electrons each. As such, this is a double covalent bond, 2 dot-cross pairs. A good thing to remember is that the number of electrons an atom needs is the same as the number of covalent bonds it must make. Hydrogen can only ever make 1 bond, carbon makes 4 bonds, etc. Here are a few more examples. If you're not in a rush, pause the video and have a go at figuring out the dot and cross diagrams and structural formula for all of these. And here are the answers. These above are what we call simple molecular or simple covalent structures, individual molecules that can all mix together. These have relatively low boiling points as there are only weak intermolecular forces between them that need to be overcome with heating. Be careful though, they're not covalent bonds being broken in this case, and unlike ionic compounds, these can't conduct electricity, even as liquids. Giant covalent bonding is similar to the lattice nature of ionic compounds. Atoms form covalent bonds to other atoms, which form bonds to other atoms, and so on, until what we have in effect is one giant molecule. Diamond is an example of this. It's a crystal of carbon atoms bonded to each other. That's why it's so hard and has such a high melting point. You'd have to break the covalent bonds in order to change it, and they're incredibly strong. Graphite consists of layers of carbons with 3 covalent bonds each in a hexagonal structure. Where's the carbon's 4th bond, you might ask? Well, the spare delocalized electrons form special weak bonds between the layers, which means that this can actually conduct electricity because the electrons can move between the layers. And it also means the layers can slide over each other easily too, which is why it's used for pencils. As a side note, it's the opposite with metal alloys. They're stronger than pure metals because having mixtures of different metals means we have different size atoms, and that disrupts the regular lattice, so layers can't slide over each other as easily. Back to carbon allotropes. Graphene is just a single layer of graphite. Fullerenes are 3D structures of carbon atoms. For example, Buckminster fullerene is a spherical football-like structure consisting of 60 carbon atoms. Fullerenes that have a tube shape are called nanotubes. Surface to volume ratio is just 1 divided by the other. If the length of a side of a cube doubles, this ratio halves. As nanoparticles are tiny, this ratio is huge for them, which means that fewer of them could be needed to fulfill a purpose compared to larger ones. Total mass of all substances is conserved in any chemical reaction. Like we said, that must mean the atoms that go in must come out, so we must balance equations to that end. We already know about relative atomic mass, but if it's a compound, we can add these up to give the relative formula mass. We just add up the individual rams, so CO2 is 12 plus 2 lots of 16, so that's 44. Some reactions produce a gas product, which, if it leaves the reaction vessel, will result in an apparent decrease in mass. A mole is just a specific number of atoms or molecules. A dozen is 12, a score is 20, a mole is 6.02 times 10 to the 23. This is called Avogadro's constant. You might need to know the number, but we don't really do any calculations with it at GCSE. Grouping particles into moles is just helpful when it comes to comparing amounts of substances, as we can't deal in individual atoms or molecules. If you have as many grams of a substance as its relative atomic mass or formula mass, you have 1 mole. So 1 mole of carbon has a mass of 12 grams. That means we calculate the number of moles of something we have like this. Moles equals grams over rams, where rams is short for relative atomic mass, but it could also be formula mass. This equation is worth remembering. Let's take our methane combustion reaction again. Like we said, in order to balance this, we'd need 2 oxygen molecules per 1 molecule of methane. This is also true for moles then too. We'd need double the moles of oxygen to methane. So here's how a question could go. How many grams of water would be made if 64 grams of methane reacted completely with oxygen? We need to get from the mass of one thing to the mass of another, so we use moles as the middleman. The process goes like this: mass, moles, moles, mass. We switch from one substance to the other at the halfway mark. So, a mass of 64 grams of methane. How many moles is that? Well, moles equals grams over rams, so that's 64 divided by 16. That's 4 moles of methane. But look, there's no number in front of the methane, but there is a 2 in front of the water, which means that we must have double the moles of water. So it's not 4 moles of water that are made, but 8 moles. By the way, we can say that the stoichiometry is 1 to 2. This just means the ratio of moles of one substance to another in a reaction. So what we have to do then is turn this number of moles back into mass using our equation by rearranging it. Put it into a triangle if you have to and cover up mass. We have grams equals moles times rams. So that's 8 moles times water's ram of 18. That's 16 plus 2 lots of 1. That's 144 grams of water made. You could also be given the mass in kilograms or even tons. The great thing is that because this is all relative, we could just put those masses into our equation instead of grams, and so long as you stick with that unit for the whole question, you'll still end up with the right answer at the end. We can also use moles to predict how much of a reactant we would need in a reaction. As you can see, we need 2 moles of oxygen to every 1 mole of methane. If we had that 1 mole of methane but only 1 mole of oxygen, well, that means that not all of the methane would react. Some would be left behind. We say that the oxygen is the limiting reactant in this case. We could also put it the other way around. We could say that the methane is in excess. The concentration of solutions can be given in grams per decimeter cubed, where a decimeter cubed is 1,000 centimeter cubed. But it's often useful to convert grams per decimeter cubed into moles per decimeter cubed instead. If 1 mole of HCl is dissolved in 1 decimeter cubed of water, we've made hydrochloric acid that has a concentration of 1 mole per decimeter cubed. Sometimes you might see this as just 1 molar, 1 capital M. Same thing, that's what that means. We know that metals vary in their reactivity as some donate their electrons more readily than others. Here's the reactivity series for the most common metals we consider. You can see that hydrogen and carbon have also snuck in there. That's because it's often necessary to compare the reactivity of metals to these in order to predict what will happen in a reaction. A more reactive metal will displace a less reactive metal from a compound, that is, kick it out. For example, if you place zinc in copper sulfate solution, you'll see copper forming on the lump of zinc. This is because the zinc is displacing the copper to form zinc sulfate, kicking the copper out of the compound. We know that alkali metals react with water. The reaction happens because, well, for example, potassium is more reactive than hydrogen, so in essence, it displaces the hydrogen from the water, leaving potassium hydroxide behind, and hydrogen gas is produced. Potassium hydroxide is an alkali, of course, which is why we call these the alkali metals. We can use this when it comes to extracting metals from their ores found in the ground. Any metal less reactive than carbon can be displaced by it. For example, iron can be displaced from iron oxide with carbon, or coke. This is called smelting. We can also say that the iron oxide has been reduced. It's the opposite of oxidation because oxygen is lost. Even if oxygen is not involved in a reaction though, we can still say that reduction and oxidation are happening, depending on whether a reactant loses or gains electrons. The mnemonic is oil rig. Oxidation is loss, reduction is gain, of electrons that is. The iron ions in the iron oxide are positive, of course, because they're metals, and they gain electrons to turn back into atoms. They become neutral. They've been reduced. Here's the half or ionic equation for this. We never really have a minus in any half equations, so think carefully about which side the electron should go on, depending on whether it's being oxidized or reduced. Metals more reactive than hydrogen can displace it from an acid too, so most metals react with acid. This always produces a salt. Alkalis have a pH greater than 7. These can react with acids. This produces a salt and water. If the quantities used are just right, according to the stoichiometry, they will neutralize each other completely to leave no unused reactants. Here's an example. Sodium hydroxide and hydrochloric acid make sodium chloride and water, and that has a neutral pH, and that's 7. If sulfuric acid is used, a metal sulfate is made instead. Nitric acid, a metal nitrate is made. These salts are left in solution, that is, dissolved in water. When any substance is dissolved, its ions partially dissociate, as does the water actually, into H+ and OH- ions. We can obtain solid crystals of a dissolved salt by warming gently so the water evaporates, leaving crystals behind. The pH scale is a logarithmic scale, base 10. It's not linear. But what does that mean? Well, an acid contains H+ ions, and an acid that has a pH of 3 will have 10 times the concentration compared to the same acid that has a pH of 4. An acid at pH 3 would have 100 times the concentration of H+ ions compared to that acid at pH 5, and so on. Alkalis work in a similar way, but with OH- ions instead. The higher you go from 7, the greater the concentration. A strong acid is one that dissociates or ionizes completely when in solution, like hydrochloric, nitric, and sulfuric acids. Weak acids, on the other hand, only partially dissociate, like ethanoic, citric, and carbonic acids. The pH of an acid depends on both its strength and concentration. So, for example, if hydrochloric acid and ethanoic acid have the same concentration, the hydrochloric acid will have a lower pH as it's stronger. Electrolysis If you melt an ionic compound, let's say aluminium oxide, it can conduct electricity as the ions can move. By passing a current through this then, using inert electrodes, that means they won't react, like carbon, the positive metal ions, or cations, that's Al3+ in this case, move to the negatively charged electrode, we call that the cathode, where they receive electrons and turn into atoms. Cations are always reduced at the cathode, so in this case solid aluminium forms on the cathode. The negative ions, or anions, O2- in this case, move to the positive electrode, the anode, where they lose electrons. In this case, oxygen gas O2 is formed. Anions are always oxidized at the anode. This is one way of purifying metals or extracting them from compounds, say if displacing with carbon isn't an option due to their reactivities. In this specific case, the oxygen produced at the graphite anode reacts with the carbon itself, so these need to be replaced every so often, so they're not perfectly inert. Again, specific for this case, aluminium oxide is mixed with cryolite to reduce its melting point, making the process cheaper. We can also electrolyze ionic substances in solutions, say sodium chloride solution. We know that this solution is a mixture of Na+, Cl-, and H+ and OH- ions, as they're all partially dissociated. But what's going to be attracted to and reduced at the cathode? Is it the Na+ or the H+ ions? Well, it comes back to reactivity. The more reactive ion stays in solution, while the less reactive one moves to the cathode. That's the H+ in this case. That's why hydrogen gas is made at the cathode here. If the metal in solution is less reactive than hydrogen, say copper in copper sulfate solution, it forms on the cathode instead, and the H+ ions stay in solution. If the non-metal ion is a halide, like the Cl- here, it's oxidized at the anode. If there's no halide ion in solution, the oxygen from the OH- is oxidized instead, and oxygen gas is produced. Any chemical reaction involves energy transfers, as energy is needed to break chemical bonds, while energy is released when chemical bonds form. Both of these happen in any reaction. If there's more energy released from bonds being made than energy needed to break bonds, we say this is a net energy released, and we should observe an increase in temperature as a result. This is an exothermic reaction. The way I think about it is explosions are exothermic. I mean, the X just means out in both words, doesn't it? If it's the other way around and there's a net energy input into the reaction should get colder. This is an endothermic reaction. We can do a practical on this. We carry out a neutralization reaction between an acid and alkali in a polystyrene cup, which is well insulated, and we put a thermometer poking through a lid that sits on top. We measure the maximum temperature the reaction reaches, then increase the volume of alkali used and repeat. Eventually, the maximum temperature won't get any higher due to all of the acid reacting, and the same amount of energy released is being spread across a larger volume of liquid. We can draw two lines of best fit for the rise and fall in these maximum temperatures, and where they meet tells us how much of the alkali was needed to neutralize the acid. We can use an energy profile to help us visualize the difference in energies between the reactants and the products. Now, this is something that people get confused with. The y-axis is technically potential energy, and you hopefully should know that usually in science, potential energy and kinetic energy do a balancing act. If one goes down, the other one goes up. So, if the potential energy of the product is less than the reactants, they must have gained kinetic energy, and that always means a higher temperature. So this must be an exothermic reaction. Just to reiterate, it might seem like the energy has gone down, but it's the potential energy that's gone down, so the kinetic energy has increased. Fuel must need a spark to start it burning, which is why we draw this bump to represent the activation energy, the energy needed to get a reaction started. Every bond needs a very specific amount of energy to break. For example, 413 kilojoules of energy is needed to break a mole's worth of carbon-hydrogen covalent bonds. If a mole of these bonds are made, though, it's the same amount of energy that's released instead. So let's take our combustion of methane reaction once more and draw the structures so we can see all of the bonds. We need to break all of the bonds in the reactants first, so that's 4 lots of 413 and 2 lots of 495 for the 2 oxygen double bonds. So that's altogether 2,642 kilojoules per mole needed to break all of the bonds. The unit isn't that important, by the way, for GCSE. We're more interested in the numbers, relatively speaking. Making the bonds on the other side, we have 2 times 799, that's released when the CO double bonds are made, plus 4 lots of 467 for the 2 water molecules. That's 3,466 kilojoules per mole released. By the way, you'll always be given these numbers. You don't need to remember them. So I hope you found that helpful. Leave a like and a comment if you did. And click on the card to take you to the playlist for all of the papers. And don't forget to check out the Quiz Shorts app to help you test your knowledge. And I'll see you next time.